Now we'll look at some examples using the alternating series test. So to begin with, let's look at the alternating harmonic series. And this was the one that we sketched out the partial sums for in our alternating series test video. The sum from k equals 1 to infinity of negative 1 to the k minus 1 over k. So to be clear here, our reference in the alternating series test to b sub k, which was just the magnitude of the terms, in this case would just be 1 over k. So when we're checking our conditions of the alternating series test, we need to verify that the limit as k approaches infinity of 1 over k is 0, which is certainly true, and also that the terms are decreasing, which we can check by looking at the k plus first term in magnitude, 1 over k plus 1, in comparison to the kth term in magnitude, which is 1 over k. Because the denominator on the left is always going to be larger, this inequality will hold true. Sometimes you'll find in alternating series test examples, there's not a lot that you actually have to mathematically verify. You do always want to write down the conditions that you're checking in the case of using the alternating series test. If you're able to simply verify that those are true right away, then it suffices to list them. In a moment, I'll go through an example where we would see that we might need to do a little bit more work to check those. Now that I've verified that both of these hold, I can say that the series that we started with converges, and yet again, I want to reference the test I'm using, alternating series test, which I'm going to abbreviate AST. A slightly more complicated example, again, an alternating series, negative 1 to the k square root of k divided by k plus 4. This is alternating, and again, in terms of disregarding the sign of the terms, I would look at root k over k plus 4. So checking my two conditions, first of all, we want to find the limit as k approaches infinity of square root of k divided by k plus 4. Notice that I have k to the 1/2 on top and k to the first power on bottom. This limit is going to be 0. However, the second condition here is a little bit harder to check. So if I'm looking at the k plus first term without the sign, this would be that term, and I want to check if it's true that that's less than the kth term in size. Unlike the previous example, I can see that both the numerator and the denominator are changing here, so it's not obvious whether or not this is true. So what I have to do is keep writing out equivalent statements until I get to a point where I can verify whether or not the inequality holds. First of all, to get rid of the radical, we can square both sides of this inequality, which would leave us with k plus 1 over, so note that this first of all is k plus 5, so this would become k plus 5 squared, and we want to verify that that is smaller than k over k plus 4 squared. Now we can cross multiply so that I can get this all onto one level, so I would have k plus 1 times k plus 4 quantity squared is k squared plus 8k plus 16. And we want to check if that's less than k times k plus 5 squared, which is k squared plus 10k plus 25. And now we can see that this is going to be equivalent to, let's multiply this out, k cubed plus 8k squared plus 16k plus k squared plus 8k plus 16. And we want to see if that's smaller than k cubed plus 10k squared plus 25k. So I'd like to combine like terms. One thing I can do is cancel the k cubed that's on both sides. Notice that I have an 8k squared and a k squared, giving me 9k squared on the left and 10k squared on the right. So if I subtract 9k squared from both sides, that leaves me with a single one over here. I have a 16k and 8k, which is 24k. Subtracting that from both sides, I have 25k minus 24k on the right, so k. And then finally, there is just the constant term on the left side. And we want to check to see if this inequality holds for k equals 1, 2, 3, etc., because those are the values the index takes on. And you'll note here that this doesn't hold for k equals 1, 2, or 3, but this holds for k greater than or equal to 4. So it turns out that this suffices. So of course, we talked about needing this to be true for all k in our statement of the alternating series test. But it turns out as long as you can show that it's true for all k after some fixed value of k, that is sufficient. Now the reason for this goes back to something we've talked about before. Remember that if I talk about the sum from k equals 1 to infinity of some term, I can always view that as the first 3 terms plus the sum from 4 to infinity of that same term. So in this example, we're basically able to show that the sum from 4 to infinity converges because both of these properties are satisfied. And we've talked about before that adding or subtracting finitely many terms of the series does not affect whether or not it converges. Certainly, it would affect the total sum of the series, but we're just interested in whether or not this converges or diverges. So, in conclusion, we can technically say both of these are satisfied. So I can say that, once again, the series that we're looking at here converges, and I must, again, reference the alternating series test. So in this example, it would not be sufficient to simply list this first inequality and not actually verify whether or not that's true. Another example, if I have the sum from k equals 1 to infinity of minus 1 to the k times k over k plus 3. I go to check my first condition of the alternating series test, which requires that I look at the limit as k goes to infinity of k over k plus 3. That limit's 1. Importantly, that means that that first condition doesn't hold because this limit is not 0. And I'll say here that I do typically list this as the first condition intentionally because once I can show that this limit doesn't go to 0, we don't even have to check with the terms being decreasing or not. We have not satisfied the conditions of the alternating series test. So we have to be a little bit careful here. The statement of the alternating series test did not say if these aren't satisfied, then the series diverges. It simply says that if both of those conditions hold, then the series does converge. So we can't ever say something diverges by the alternating series test. However, if you can show that the terms in magnitude are not approaching 0, then what we really can reference is the test for divergence. So certainly if I threw a negative 1 to the k into this limit here, that too would not approach 0. So we can say that the series diverges, but what I reference is not the alternating series test, but instead the test for divergence. And I want to look at one kind of strange example, and this is based off of questions that I typically get asked in a face-to-face lecture. So here, suppose we're asked, does the series 1 over 2 squared plus 1 over 2 cubed minus 1 over 3 cubed, I meant to make this alternating, 1 over 2 squared minus 1 over 2 cubed plus 1 over 3 squared minus 1 over 3 cubed plus 1 over 4 squared minus 1 over 4 cubed, and so on. Does this series converge is the question. So I can see that it's alternating. So this series is alternating. And I could definitely say that the limit as k approaches infinity of what I've referred to as b sub k, as ignoring the sign. This is certainly going to go to 0. Notice that these terms are approaching 0. But if you look at the second condition, it's not true that each term is less than the previous one in size. And not only is it not true for all k, unlike our second example above, there isn't going to be a fixed value of k after which point it's true. If you were to think about plotting the terms of this series, again, ignoring the sign, you'd get kind of a zigzag pattern. So it's trending downward, but not every other term. So what this means is that we can't use the alternating series test. We certainly can't use it to say that it converges because it doesn't satisfy both of these conditions. And like I referenced in the last example, if these two conditions don't hold, that doesn't mean that the series necessarily diverges. In particular, this series converges. I just can't use the alternating series test to say that that's true. So what we can do instead is look at the individual terms, and you can actually think about splitting this series into two different series. So I can look at the positive terms and notice that I have a pattern of 1 over, here we go. I have a pattern of 1 over 1 over k squared. So this series can be written as the sum from 2 to infinity of 1 over k squared minus, if you look at all of the negative terms, likewise this starts at 2, but these are 1 over k cubed. Both of these converge, right? They're p series with p greater than 1, 2 and 3 respectively. And so their difference will converge. So the original series converges. And again, the purpose of this example is to kind of point out, in the past I've had students ask, understandably, how is it possible that a series could have terms approaching 0 in size but not be decreasing? And so we see here the idea that this is trending downward, but every other term we have this kind of zigzag pattern here, and so I would not be able to apply the alternating series test. In that case, we have to be a little bit more creative. Here we came up with an alternative way, and it turns out that we might be able to use what we'll cover soon, which is called the absolute convergence theorem. So that's going to be something that we can start to consider for series with negative terms. And the nice thing about that is that won't even require that the series be alternating, just something to use as soon as we start to encounter negative terms in any form in our series.